Welcome to our talk today on healthcare application security. My name is Seth Foge. I've been doing security in various forms and functions for about 20 years, the last 10 of which have been with Penn Medicine, really specifically focused on healthcare applications and embedded in the healthcare security environments with various healthcare organizations. So a point of reference, 16 years ago, I happened to be presenting at Black Hat. That subject was on pocket PC abuse. A few things have changed since then. I've got less hair, got more kids, and pocket PC really isn't a thing anymore. But it's kind of underlying architecture, Windows CE still is actually in use inside of the healthcare environments. Along with HL7 and DICOM, these particular subjects have been of interest and have gotten a lot of attention. I just want to give a nod to those people who have been doing research on that, including one of our very own at Penn Medicine, Dr. Ben Wall, who's been focused on DICOM security. But this talk is not about those things. Instead, we're going to be focused on the application security. And by application security, I mean those applications that deal with the patient records and the patient workflows that really kind of address a definitely concern in the security field, and that these are actively being exploited and the patient records are being sold, and there's a real monetized value about these things. So on that note, these are one-day vulnerabilities in that vendors are aware and certain members of HISAC are aware, as we try and get awareness around that. But there's no guarantee that the patches have been deployed if there's even patches available. So as a result, the vendor names and products are going to be censored from this talk, thus the fuzzy screen. However, certain goals we do have today. And the first is to really bring awareness to healthcare security professionals on some of the methods and things they can look at in their own environment, as well as bring attention to the vendors as to what we don't like to see in their software so they can proactively remove this kind of stuff from their solutions. And then finally, provide some insight to the security community, what they can be looking for, whether they're assessors or auditors or pen testers, to help really raise the bar when it comes to healthcare application security. Now, we can't have a talk about security without Alice and Bob. And we're going to be using Alice and Bob in a kind of a fictional overlay and a fictional context as they are interfaced with the Black Hat Clinic. Now, conveniently, the Black Hat Clinic is about the same size as Penn Medicine, so there's some correlation there in the numbers. But again, this is going to be a fictional overlay with some fictional elements using Bob and Alice to really drive home the patient perspective, because we can't lose fact that there is a patient behind all these technical issues ultimately, and we want to make sure that patient care is one of the key priorities here. So, Alice and Bob have been with us since the 70s. In the 80s, apparently, they went through some kind of divorce, something to do with lack of communication and keeping secrets. But they were able to get reconciled and have grown old with each other over the past, 40, 50 years, and now in their 60s or 70s. With age comes some healthcare issues, and Bob is with us now at Black Hat Clinic, where he's getting his pancreas taken care of and some analysis done there. He also has diabetes, and Alice is beside him and helping him through this process. So currently, Bob is off getting this procedure, and Alice is sitting inside of his room doing what most loved ones do at this point, watching TV. And at this point, we're going to introduce Mallory. Mallory is the bad guy in this kind of fictional overlay. He's the one that's the threat, and he's kind of interjected himself right on Alice's screen with this message that kind of really throws Alice off. Now, Alice is a security person. She understands that there's risk here, but she also knows who to contact, and she contacts the security team at Black Hat Clinic, and we come in and start talking to Alice about this particular system. Alice's first question is, this is a TV. How is somebody able to take over this TV? And we want to clarify that, and that Alice, this isn't really a TV anymore. This is a patient entertainment system, meaning it's a system that has all kinds of integrations behind the scenes to not just entertainment, but to meal ordering and education and nurse call systems. In addition to that, it does have a screencast feature, which allows doctors to take their screen and throw it up onto the patient screen or to their patient device. So it looks like Mallory got into this. Now, we're going to take a look at that, because from a bad guy's perspective, if Mallory's in there, he can obviously impact the patient experience, but also potentially access patient records. And as you're experiencing, Alice, it can raise some stress issues, and also there's some potential issues about data and security privacy. So we take a look inside of our application database of about 250 applications and find the application listed there and get it installed, and note that it's a client server architecture with some web interfacing behind the scenes. So we integrate Burp into this, which is a good proxy program. And when we launch the program, we're expecting to see some kind of authentication prompt, but no, we come right to the screen. We can see Bob's room there, room number 5, no authentication. So we want to see what happened behind the scenes. We take a look inside our Burp records, and the logs there and see that there is indeed a web request. No authentication in this web request, but more concerning, it returns a whole lot of XML, and this XML contains date of birth, patient name, patient number, room number. And it's important to note here that this is kind of setting a line in the sand and hitting a bar that we don't want to ever see, and that it actually sent more than 500 records back. And that's a kind of a line in the sand, because when you get above 500 records, and if this was a breach, it would be posted to a wall of shame. There's potential investigations. Actually, there will be investigations with potential fines. Not to say that less than 500 records isn't important, definitely for patient safety and privacy and security, and also that it may not get some attention, but that 500 line is definitely a mark in the sand. But that's not how Mallory got access to the screen. So we go back to the program and hit Bob's room number, and it comes with this prompt. Enter the number 1234 in there. And we look behind the scenes and don't see anything that's being passed from the client to the server, which is unexpected because we would expect to see that authentication occur. So we do take a look, and we see that there is a WebSocket upgrade request, and inside that WebSocket data, there is a reference to this 4-digit number here, 9284, which we plug into the prompt, and sure enough, that allows us to know the screen. So in this just basic kind of simple example, we kind of illustrated that there's some unauthenticated API requests that are able to allow you to retrieve over 500 records, and there's no validation other than on the client. So you got a client created pin, a client validated pin, and really the pin's only passed to the server just for informational purposes. So not very complex, definitely a high issue, and we got patient records over 500. So we got what we would consider a high risk issue in this case. Now, we start reaching out to the vendor, and we talk with our internal team and realize that we can probably just disable this feature and get rid of it altogether. So we go back to Alice with these findings and explain to her that, well, we figured out what was going on, we're shutting it down, so we're gonna get that taken care of. At this moment, the doctor walks in and says, well, Bob is done with his procedure, and we're documenting everything up, and we're getting prepared for the documentation you can take home, so you know how to treat Bob at home and what you can do afterwards, and making sure that everything's properly proceduralized away in the system. We'll be back then very soon with some more information about his MRI system. And doctor walks out, and Alice turns to us and says, well, Mallory's already threatened us. Is this something that he could take advantage of? And well, we tell Alice, this is a system that kind of captures all the procedural parts of what occurred and allows a physician or clinical care team to provide instructions and follow-up workflow. There's auditing capability built into it. There's a lot of really important information here. So yeah, if Mallory was into the system, he could access the information at a minimum and maybe modify it, which could be a problem because from a patient perspective, that could lead to a misdiagnosis. It could actually lead to higher costs for care because there's coding, which ties to insurance. There's also definitely the loss of data and privacy security issues. So we tell us we're going to take a look, pull up our application database again, and this time we have 300 applications now. We're digging through and we find the application, get it installed, and start a different approach on this one where we're going to take a look at the code that represents the client software. And we like to do this because we sometimes learn a little bit about how the program operates by just investigating how the logic of the code works, some key functions that might be in there that indicate there's some issues. In particular, we're going to use dnSpy. It's a freely available and really great tool that we'll use a couple times in this presentation, but we look for keywords like encryption, backdoor, seed, secret, username, and it's really up to the tester to kind of build their own library. But in doing this, we end up drilling into the program. We find a point called validate user and password. Sounds interesting, so we drill down into it, get to the snippet of code, and at this point we notice two particularly disturbing issues. One is that there's a backdoor reference, and the other is a daily password function. We drill down into the daily password function, and at that point, we see the snippet of code here that we can basically just copy out, drop into an online site called .NET Fiddler, and hit the run button, and it produces a 8-character value. This looks like a password of sort, so we take that username backdoor, and we take the password that was just generated, plug it into the client interface, and bang, we're now into the system as a backdoor account with full access to all the data, all the information in there for all the patients. Definitely a major issue that we discovered here. Now, in addition to that, we did find several other issues that are equally as bad, but really end up with the same result, in that the system's fully compromisable. The complexity is not that high. The impact is definitely pretty significantly high. But what frames this a little bit differently is we got over 100,000 patient records now that are potentially exposed to this particular bug. So we go to the vendor, and the vendor recognizes the issue and starts remediating it and looking for how to fix the problems for their clients. We go back to Alice and tell us, well, it looks like there were some bugs there. We don't see any indication that Bob was in there messing with anything. We're double checking and making sure that nothing happened to his record. So at that moment, the nurse walks in, and it's time for Bob, who's back from the procedure. He's lying there. He's got a little bit of pain. Nurse comes in with some drugs. Alice stops her and just takes a look at the drugs, notes the number stamp on them, and allows that to go on because Bob's got some allergies. So knowing that, Alice turns to us and says, well, he got allergies. How do I know that Mallory couldn't end up impacting like the drugs? Could he mess with something in that system? So we tell Alice, well, this is part of a bigger system. It's a drug dispensary system. We've got centralized medicine management that allows you to distribute medication out to the floor where it needs to be closest to the patient. But integrated into that is a lot of automation, a lot of auditing, diversion control, which is theft control. So, yes, you're right. If Mallory did get in there, he could do something. He could access patient records, modify the drug information, maybe even steal drugs. From a patient perspective, that could lead to drug misoverdose or the wrong kind of drugs, which could be an underdose as a result of theft. In addition to that, there's the patient privacy and security issues. So again, we take a look at our application database and we tell Alice that we're going to take a look. We're up to like 400 applications now. And we just find the application, and in a quick look at the server, we see that there's this open share file that's part of the application install. It's an authenticated user share, which means anybody on the network who's authenticated can get into the share. Exposed in the share are two kind of issues. One is a configuration file, which you have a snippet here on the screen you can see. The second is that you have a bunch of binaries. Now, we kind of illustrated in the last issue that if you have the binaries, you can get a good understanding of what's in the program and how it operates. So we drill into the program, start taking it apart, and start focusing on the SQL account decryption first. And note that there is actually a function there called decrypt SQL credentials. What's important about this is we've got the code, and since it's in a DLL, we can really just take all the functionality of that DLL, import it into our own Visual Studio.NET file, program, and have access to that functionality. And really within one line of code, decrypt that value that's in the config file that's open to the network. So we do that, find out it's the SA account for the database, and it has a password that appears to be a pretty much probably is a vendor default password. But still, we have that account, and we go back to the user accounts this time, and we start looking at what we can do there. Now, in this case, the decryption functionality is in some exe files, so it's not just a matter of referencing a DLL, but we can still copy out the hard-coded AES value and the algorithms used to decrypt these strings, and still paste them and piecemeal them together in our own Visual Studio.NET program. So we do that, and we discover that inside of these encrypted values is a local administrator account for the server, as well as some other key critical accounts for the application. So in other words, we have full system access to the database, full access to the server. We take a look inside the database now and discover that there is a user table and there's usernames, but there's also a bunch of passwords that are encrypted. Do a little testing on those encrypted passwords and discover that's the same encryption algorithm used to encrypt the user accounts from before. So we run through and decrypt all those accounts as well and discover that there's a bunch of vendor accounts in there that have the same default password. In addition to that, we really have just compromised the whole entire user table database. So we take that information and now actually log into the application interface and gain access to the drug distribution tool that's used to basically put medication in the cabinets, control the medication in cabinets, tell us what medication is in the cabinets. In addition to that, we can add ourselves as a user to the whole entire application backend at any level of permissions we want. And to make a long story short, we now have access to one of the patient cabinets as well, or sorry, the drug cabinets as well. And we decided to get some acetaminophen for the headache we now have. Just kidding, we wouldn't actually do that at Black Hat Clinic. But still, at the end of the day, we have fully compromised the system and the server. And again, we have over 100,000 patient records in here. The complexity really wasn't all that high. The impact is definitely high. So this is again what we would consider a high risk issue. Oh, we immediately contact the vendor. The vendor starts making changes right away, and there's some simple changes that can really reduce the risk of this, which are put in place. We tell Alice about this, and Alice is thankful. She understands that there's issues, and it's good that we're on top of it and making changes here. But Bob has an insulin issue. It's related to his diabetes, and she asked the question, I think insulin is supposed to be kept in a secure, safe environment when it comes to temperature. Do you guys have a temperature monitoring system on that? And is that something Mallory can mess with? Well, we tell Alice that we do have a temperature monitoring system. It's part of a overall system that monitors our drugs, our food, and blood in the organization. And it's used in many different industry types. But yeah, if Mallory were to get in here, he could disable monitoring, he could break the monitoring, which could in turn have an impact on patient safety, and that they could get poisoned or ineffective medication. But we tell us we're going to take a look, because this is, again, another critical system to patient care. So we pull up our application database of 425 applications now, and in this case, we installed a client, but we're going to take a little bit of a different approach and start to look at the data traffic behind the scenes, because this isn't just a standard web kind of ish client server architecture. So we get ourselves a test account and plug it in and run Wireshark behind the scenes, and immediately start to notice that there's a pattern. Typically, what we see is that there's a integer value followed by a couple variables which then result in a return data. For example, we have 12 as an auth code, we have 34 as a change password code, we have 67 as an add update user code, 42 as a get group detail code, and we kind of build out this library here, and we kind of just want to test this out in our own little program and see if we can just simply throw the request at the server using something like Scapy. So we create a Scapy script, which allows us to send raw data right to the server interface, and put this together, see if we can query back our own user account, and sure enough, we end up with our user ID, the username, and the password that we had set up. And yes, the password is Alpha1, not a very secure one for this testing experiment, but still, we get that password. Now, we don't have to use Scapy. We can just simply use a netcat command, essentially, and we try and test out what we can get from the administrators group. And sure enough, we end up with all the usernames and passwords of the administrators group as well. So we take that administrator account, we log into the server, and we see that there's actually an IoT monitoring device that appears to be offline. This is suspicious because it is associated to where Bob's at in the organization. So we get the IP address out of the system, connect to this little IoT monitoring device, which collects the data for various different temperature monitors. Notice there's a simple login password, but we take a look at the HTML, see there's a reference to this dub directory. Take a look at that directory. It's got file indexing enabled, and we can see that there's some Perl files here. Drill down inside those Perl files, and sure enough, there's yet another password of the day function here in a completely different program. Seems that this is a not so uncommon thing to find. But in addition to that, we also have a reference to a hard-coded cookie value that can be set and gives you administrator access to the IoT device, hard-coded in these Perl files as well. We use our cookie editor, just simply set that value in there, refresh the web page to the IoT device, and bang, we're now in. So, I mean, this is starting to feel like a capture the flag or some kind of SANS event where you're following through in some pretty stereotypical hacks. So we're not so surprised to see a ping out test here. And one of the more common ways that those type of tests can be exploited is to simply concatenate another command on the end of the IP address, which we attempt to do with the cat etc password file, which should return the whole password file. Of course it does, and we now have passwords for the IoT device. Take those, throw those into John. In about 2 seconds, we end up cracking one of the passwords. It's not the root account, but it is one of the passwords to be able to allow us to SSH into the device. Once we're in the device, we start looking around, and in there there's an index.cgi file. Now that file is the main page that is used to piecemeal all together the web requests, and we find this reference to a run su command. Now that looks suspicious because it looks like it's going to give us the ability to run a super user command on the system. So we swap out one of those values there, and we will actually just add our own. We're going to try and run a reverse shell and get that reverse shell pointed back to our server. We refresh the index.cgi page, and sure enough, we are now have root access to the device. Since it's not working anyway, we ask permission to reboot the device, reboot it, it comes back online, so it looks like more of a false positive, just a glitch in the system. But at the end of the day, we still have unauthenticated access to the server, gain administrator account access, and IoT device as well. We have full system control of both of those parts of the application. Now, there's no patient records exposed, but this is a compliance and kind of regulatory issue. Wasn't very complex. The impact is, we'll rate it a little bit less higher because there's no patient records, but still in a zone that we don't like to see. Oh, we go back to Alice and we tell us that we're going to be actually architecting this kind of off the network and segment this whole system out so we can reduce the risk for this environment. Again, Alice thanks us for our work, and at this point, Bob mentions that he's a little hungry, and so Alice picks up the nurse call system and kind of pauses and says, this nurse call system, is it just going to ring a bell, or is there more to it? Well, just like the patient entertainment system, these have evolved over time as well. And they're kind of baked into a whole back-end environment where we can basically monitor the resources that are used across the organization, from who's the most needy patient to how fast as nurses can reply, and help us allocate where resources need to be put, as well as tracking devices and nurses in that whole entire process as well. So from Mallory's perspective, he gained access. He could probably get access to patient data, take over the nurse call system, locate patients if it has RTLS enabled. From a patient perspective, they could end up getting woken up repeatedly at 2 a.m. in the morning if somebody wanted to be really pain and start doing nurse swatting. In addition, there's the loss of data and privacy security issues. So we take a look at our application database, and if you haven't noticed, this is growing, which is indicative of what is happening in healthcare. We're seeing more and more applications being thrown onto the stack to provide all kinds of different functionality. And a lot of these applications have some really great use and some key patient care value, but the stack keeps growing, which means the security teams have a greater risk exposure as well. Well, in this particular application, we get it installed, and we're going to take a little bit of a different approach because it's got a client and a server, but we want to see if maybe this client has some logic errors that really allow us to completely bypass authentication altogether. So we drill down inside of it, and on the left side of the screen, we have the logic flow of the program. You can see there, it basically throws the password and the username off to the database, and the database returns an integer value. One of the values is sitting in the table there on the right. So looking inside that table, we see that there's some values there, but in this case, we want to take the program and debug it. And again, there's a couple different ways to do this, but .NET Spy makes it very easy. So we simply connect the application to it. We hit the debug button on the menu and start debugging the program. And this gives us the ability to watch the program work in memory and see the values that are actually being passed around in variables inside the program. So we drill down on the verify login function here, and you can see in little small type there's an admin account, the password ASDF. We let it flow through the program, and at the bottom there, it returns a result. Now, that's not the right password, and in addition to that, the account appears to be locked out, so it's returning that integer value that's associated with the account being locked out. But we can change that value, so we can just go in there and switch it to a 0. And we could do this every time we restart the program, but since we have the capability, we can also just simply modify the binary and make this value hard-coded so it always returns a 0. No matter what password you then enter, it's going to be valid. So we do that, we save off the new binary, and we relaunch the application, use the username admin with whatever password, and bang, we're now into the system as an administrator, which gives us the ability to control all the user accounts and basically make nurse calls to any room, any floor, any bed we want to. Now that's definitely a big problem, but we also note that there's a server-side component to this. We just want to take a look at the server side. We're going to drill in a little bit and see what kind of references using that same example we used in the clinical documentation system to see if there's anything important in there. And we do that. Here's the user interface, and while we're looking around, we happen to find a reference to a backdoor account. Except not just one backdoor, 3 backdoors in this case. And this is a little bit interesting because we go back to the vendor, and the vendor's basically kind of stuck because this was part of a merger and acquisition where they've kind of acquired some of this code and don't really have the capability, at least to really fix it. They're going to focus on a new version. So, we've got the capability to patch it. So instead of asking the vendor for a patch, we've looked into patching it ourselves and just simply changing those passwords to something a lot more complex and not so standard. And we do that, reboot the program, it comes back up, and now we've patched our own issue regarding this backdoor. But we have access to the administrator interface of the nurse call system. all the patient data that's flowing in between, and the ADT feeds are called. At the end of the day, the system's fully compromised. Wasn't really that complex, and the impact's definitely high. We're over our 500 count, and this 500 count's a little bit of a fuzzy number because it's a per day account, maybe a per week account, and that number is going to grow over time as more patients come through the system if somebody was actively monitoring, or it's going to be a snapshot in time if somebody just found this issue at point of exploitation. So we go back to Alice and tell her that, we found some issues. We're working to get those remediated, segmentation and patching. Alice replies, thank you. And at this point, the doctor comes back and says, well, we took a look at the radiology images and everything looks fine. We just need to make sure we keep an eye on Bob, but we're going to wrap this up and you'll be able to get out of here soon. So Alice turns to us and says, what's this radiology system? Is that another system that potentially could put Bob at risk if Mallory got in? So we tell her, well, this is a clinical imaging system. There's numerous ones out there. This one, they kind of all serve the same general purpose in that they allow you to look at the images and analyze them. They have baked in tools for analyzing, track the images over time, allow you to document against it, and share that with other radiologists and doctors. And if a bad guy got in, yes, they could access it, they could modify, they could delete. Obviously, that's going to have potential to impact patient care from Bob's perspective, in addition to the loss of data and privacy security. So we pull up our application database of 500 applications now, find the application, get it installed. And this time, it's not a .NET program, but we want to make sure that we still take a look, and we use IDA, which kind of allows us to do much of the same thing. We can search through the program, find key elements that are important in there, and we do that and find a reference to password match hash and password is valid, and we start to look at those. And in addition, we can still also patch the program. It's a little bit different inside of a C++ or a C compiled program, but at the end of the day, there's opcodes that operate behind the scene, and these opcodes work kind of the same way. And in the current program, there's a jump not zero, which basically says that the password doesn't match, go this way. If it matches, go this way. We can change that to a jump zero, which means if the password matches, fail. If the password doesn't match, open. So the difference between the two opcodes is really just a 75 versus a 74, which we can find in the binary. We swap that out, save it off, have a new binary, and we have the old and the new now that you can see on the screen here from a jump not zero converted to a jump zero. And as a result, when we go back to the program, plug in this user account of support, which is provided to us as a result of some other issues with the system. We plug in a password of A, and sure enough, we're now logged in and are able to see Bob's records. But we don't really know what this means. At the end of the day, though, it still is exposed. In addition to that, because we patched that particular part of the program, it also allows us into the administrator tool with the same support account, and we can access to all the users and change their passwords, change the configuration of the system, and so on. So the system's fully compromised. The complexity, it may be a medium, but it wasn't super complicated. The impact is definitely high. And in this case, we've got over 1,000 records just because the program is a little bit more of a niche program. So we go back to Alice. We also work with the vendor before that, and the vendor is going to get us a patch for this and remediate the issue. Go back to Alice and explain what happened. And Alice thanks us for all the work that we've been doing related to this application security, raising the bar for this, getting some vendors to pay attention to the software issues. But she asks an additional question and says, well, you guys are working with these applications. They all sit in a data center somewhere, and I know you're working on the confidentiality and integrity of that CIA triad, but what about the availability? What if that data center goes offline? How are patients able to maintain their care, and how the patient care team's able to know what the patient's even there for? We tell Alice, well, this is part of an EMR downtime device solution, because you're right. You have an organization, all the databases and the software runs in the data center, but there are some times where the network goes down or a piece of hardware goes down and kind of isolates a piece of the network, whether it's an outpatient facility, a small hospital or clinic, or even a floor in the hospital. But we have these things called downtime devices that we distribute throughout the organization, and they have enough information on them for the patients in those in those areas that allow the care teams to maybe know allergies, what the patient's there for, key critical things that they need to understand about what the patient's, that they need to know in order to treat the patient. These are sensitive, obviously, so we encrypt the hard drives. They have username and passwords in them, for HIPAA compliance, and the patient reports are encrypted. The user, everything, the user table is encrypted. So Alice just kind of stops and pauses for a second and says, well, you've kind of illustrated that client-side security is really hard to do, and these all kind of sound like they're self-embodied clients that have all the data in them. We pause. You're right, Alice. So, we're going to go take a look at one of these, and we pull up one of the downtime devices and find a login prompt and start taking a look at the code behind the scenes using the same process before with DNSpy. Find a part of the program there that the password is basically doing a matching validation, and from there we strip that out and resave the binaries, and we basically set the program up so all it checks to see if the user is locked. If the user isn't locked, we find that we can gain access to the patient records inside the downtime device. Now, that's a small subset of patients, but while we're in there, we also happen to we notice that there's a load and decrypt user table function in there. So again, if it's pulling those values into memory, then we can probably take the opportunity to write those values out, and we patch the program again to just simply write the user table out using just some more C# code and plug it in there, save the binary off, relaunch the computer and program, and it gives us a copy of the user table. Now, the user hash kind of looks like this. It's got pieces of information in it, but again, we have access to the code that we can create our own, basically, representation of how the hash is created when it's entered from a username and password perspective. The hash has to be created so it can be bounced against the table there. So we recreate our own hash creation process and effectively allow us to do a hash cracking type of program that we can do offline. It's important to note that inside the user table is a copy of every single EMR user's username and hash, which is a pretty significant number of the employees at Black Hat Clinic. But we do that and we run it through, and sure enough, after a few minutes, we discover that we can actually crack some of the passwords. It's slow, but it's offline, and it's just a matter of time and resources. And while doing that, we kind of took a step back and realized that we had another issue here, in that the authentication prompt sat in generic user space, but it interfaced with a service account running in system space, which was using DLLs that were in that's effectively generic user space and has the ability to be modified and written to by authenticated users again. Meaning we have a traditional DLL injection or overwrite issue that has been allowing us to do some of these rewrites and patches in the first place inside of the application on the downtime devices. So we take advantage of this, and there's many ways to do this, but we simply just patch it again and point it to a batch file, which gives us the capability to run any particular script or program we want. We just want to get admin on the box, so we just put in a command to add admin, and we now have admin to the box. And once we have admin on the box, we can now configure the downtime device. And we do it, the first thing we do is we configure the downtime device to basically be a downtime device for the entire organization, which means all the patients and all the other pieces and parts of the organization, all their records now also come to just this one downtime device. So we get all those records. And while doing that, we kind of discovered that there's a key that syncs the downtime device to the downtime server. It's the same key for all the downtime devices. So it's a per organization key. Now the key is securely stored on the downtime device, but because we have access to the code, we're an administrator now in the box, we can, again, just simply find the location in the program, export that key out, and now we've got a process by which we can export a key out for the downtime devices for an organization. So we go down the street to DEF CON Clinic, and we see if this is actually going to be something that can be exploited. We take our patch DLL, throw it into a downtime device in DEF CON Clinic, reboot the device, and it produces a key for us. We've got the key. We have our device here. We've managed to get it on the network, which is the first hurdle to overcome. Not necessarily a really difficult hurdle. So we get that our own downtime device, like a fake one, a spoofed one, onto the network. Insert the key into that downtime device by just modifying memory, patching it, a couple different ways we could do that. But the downtime device now has that DEF CON Clinic's key, point to DEF CON Clinic's downtime server, and now we have all the records for the DEF CON Clinic as well. In addition to that, we already know how to bypass authentication, so we don't need to worry about actually logging into it because we can just do that. And the part of the information downloaded is also the user table for DEF CON Clinic, so we can now access the user accounts and the passwords there. And as a result, we've basically expanded our scope of compromise to other organizations with this particular issue. So again, the complexity is a little bit more challenging, putting everything in on the table. The impact is definitely high. 13,000 records exposed in our scenario here. And again, this is a kind of like a per day or per patient while they're in the organization rolling number. So that number kind of could grow over time or just be a simple snapshot as if somebody were to exploit this bug. So, I mean, kind of wrapping it all up, if you look at what we did, we started with something simple, relatively speaking, with Burp, looking behind the scenes, noticing that there's just client-side code with client-side validation. Then we started looking at some of the code and seeing if there's anything suspicious in there that's hidden away inside the code that could be exploited. We also looked at some of the TCP protocols and the activity on the network, looked at how we could modify some of the logic behind the scenes for .NET programs, and then also use that for our C++ program, and patched the program and kind of wrapped it all up in a final example with the downtime devices, where we took that kind of to the next level and just showed how far you can get with one of these particular application security issues. So the reason why this is, again, important is that, just in our example here with the sizing of Black Hat Clinic and DEF CON Clinic thrown in there, we effectively were able to illustrate a compromise of about 225,000 records. Now, these records can go for, depending on who you talk to, $1,000 or $10 a record. Either way, we're talking about 2.25 million or 225 million for just one ecosystem or one environment. Now, if we extrapolate that out and you look at all the hospitals inside of the country or even broader, I mean, I could have probably named this the $1 trillion healthcare application security issue, because we're talking about some pretty significant numbers when you go that big of real data records that have a real value out there in the real world. So some pointers that we do go through when we look at these applications is we just kind of spend 2 to 4 hours looking for what I'll call red flag indicators. Default credentials, plain text credentials, some badly designed APIs with no credentials, or secrets that are embedded in code, really kind of help us understand where we may need to pay more attention and dig in deeper. In addition to that, we have found many cases where the credentials themselves are stored in a database, but we are told that the credentials are secure, but when we actually reverse out the way those credentials are secured, they, number one, aren't really that well secured, and number two, often have really bad passwords and password management baked into the program. So these are all the different ways that we look inside the organization, and we do this during what I'll call light pen tests against new products. In addition to that, because we want the team to continue to grow their skills and have an understanding of the security issues that are current, even past, or even that are coming up in the future, we do team-based pen test exercise practices where we let the team play on capture the flags or internal products or even self-developed ones that some of our team have helped create. In fact, this won the CSO 2020 award for just pushing that bar a little bit further. We have the security testing baked into our goals. We have a program for our team that again encourages them to learn more and understand more about these bugs. We also are working with HISAC, which is a healthcare consortium for those in the healthcare field to share information. And we're moving in that direction where we can share some of these vulnerabilities, because that is a big challenge for healthcare. Is we don't want to just post this stuff out there publicly when we find it. And it's hard to kind of get traction sometimes on getting remediation moving. But we want other healthcare providers to understand that there's some risk inside their network as well. And if they have the same product, they probably want to do something about it. So we're looking at leveraging HISAC for that particular aspect of this. And I mean, finally, where to from here? Healthcare security teams, we encourage you to start using some of these tactics and methods to kind of look through your own security software or own applications for security issues. We would like to be able to share, if you want to remember HISAC, that seems to be a good place to do it. It's more of an enclosed environment, and we just really need to share a lot more. Security community, I ask that if you guys and women have an opportunity to get out there and when you're doing audits or assessments or pen tests, and look at the applications. Just don't look at the how Active Directory works or just the normal stuff that you look for in a pen test. Add in the scope a healthcare application, and you might find something interesting and different instead of just going domain admin. And finally, the healthcare vendors. I mean, us healthcare security professionals already have multiple hats in many cases, especially for smaller healthcare organizations. We also have to maintain all the normal things that the security teams have to do with firewalls and end users and training and maintaining a secure edge and patching and all that. This healthcare application issue just makes it that much more challenging to keep things secure. And at the end of the day, we're really talking about patients and patient care, and that this is in many ways, a patient data and privacy security issue. So I'd just like to thank the Penn Medicine security team. Everybody on the team has had some impact on this presentation. In addition to that, I'd like to thank Black Hat for making this possible. And with that, I'll take your questions inside the chat channel. Thanks. Hello. I only have 10 seconds to really say a thank you for all those who have been interacting with me on the chat there. I'll be around in the chat for another 20 minutes or so. Thanks for the questions. Thanks for the feedback. I hope this is enlightening and brought some really much needed attention to healthcare data or healthcare application security. So thanks, and hope to talk to you later.